A 10-minute warning on the San Andreas Fault could stop trains and open firehouse doors, but science cannot yet issue one before rupture begins. Why can seismologists map dangerous faults and still not predict the exact earthquake before it starts? An earthquake prediction is not the same as saying California is risky. A true short-term prediction has to name the place, the time, and the magnitude before the fault breaks. A statement that a section of fault may produce a large earthquake someday is a forecast. It can be useful, but it is not a warning for Tuesday at 3 o'clock. The solid ground is not still. GPS stations measure the Pacific Plate sliding past North America at roughly 5 centimeters a year near the San Andreas system. Fault maps show where past breaks have reached the surface. Seismographs record where the crust is cracking now. From those measurements, hazard maps estimate the chance of shaking over decades. That is established science, and it shapes building codes, insurance models, emergency planning, and bridge design. The hard part begins below the map. A fault is not a clean cut through glass. It is a rough surface running through mixed rock, crushed zones, fluids, and locked patches. Stress builds across that surface, but the most important stresses sit kilometers underground. They cannot be read directly at the scale needed for a prediction. The missing piece is the one a prediction needs. Which locked patch will fail, when it will fail, and how far the rupture will run. Rupture is a cascade. A small patch slips first. That slip can load the patch beside it, and the break can grow into a damaging earthquake. It can also stop after a tiny tremor. The difference can depend on friction, fluid pressure, rock damage, and the shape of the fault surface. Those conditions vary over short distances. The physics is not magic, and earthquakes are not random in the everyday sense. But the starting conditions are hidden and uneven, so the final trigger is not measurable enough for a deterministic forecast. Parkfield, California, became the clearest test of the hope that repetition might be enough. A section of the San Andreas Fault near Parkfield produced magnitude 6 earthquakes in a pattern that looked unusually regular, including events in 1857, 1881, 1901, 1922, 1934, and 1966. The average spacing was about 22 years. On that basis, scientists expected another similar earthquake before 1993, and they heavily instrumented the area. The earthquake did come, but not on schedule. It arrived in 2004, about 38 years after the previous one. Parkfield was valuable because it recorded a fault in unusual detail. It also showed that a pattern in past earthquakes was not enough to predict the next rupture time. Earthquake early warning solves a different problem. Systems such as USGS ShakeAlert do not predict rupture before it begins. They detect the first seismic waves after an earthquake has started, estimate its location and size, and send alerts before stronger shaking reaches places farther away. The warning may be seconds, or in favorable cases, tens of seconds. It may be too late near the epicenter. This is still useful. Trains can slow, surgeons can pause, elevators can open at the nearest floor. But the system is listening to an earthquake already in progress. Many proposed precursors have been studied, including unusual animal behavior, radon changes, cloud patterns, and earthquake lights. Some individual observations may be real physical effects. The problem is reliability. An operational prediction method has to work before the rupture, often enough to trust, with place, time, and magnitude attached. These signals have not met that standard. They produce misses, false alarms, or patterns that appear only after the earthquake is already known. The answer is that seismology can measure the slow loading of faults much better than it can measure the exact underground state that decides failure. Long-term hazard maps are real. Probabilistic forecasts are supported by plate motion, fault history, and seismic records. Early warning can reduce harm after rupture begins. What is not currently possible is deterministic short-term prediction, naming the exact place, time, and magnitude of an earthquake before the fault starts to break. That may change only with measurements that can see stress, friction, and fluids deep underground at the scale where rupture begins.